Hey, welcome to Passages in Applied Mechanics by Dr. Lorenz Garcia. Today, dynamics, and the impulse-momentum method in dynamic systems. This method is based on the concept of linear momentum, and on the related physical quantity called impulse. For this reason, we often refer to it as the impulse-momentum method when we use it to solve certain engineering problems. Momentum is a concept used in mechanics for the solution of specific problems which are difficult to solve by the force acceleration or by the work-energy methods. These problems usually involve direct relations between force, mass, velocity, and time. Let us start with a few definitions first. Momentum, sometimes described as the quality of motion, is the product of the mass m of a body and its velocity v at any given instant. A similar concept, called angular momentum, may also be used in rotational dynamics where it is expressed in rotational terms, but for now, and with not special symbol, we can consider momentum as the equal of mass times velocity. Notice, unlike energy, momentum is a vector quantity. In other words, it has a direction that corresponds to the direction of the velocity. Attending at the definition, what is the unit of momentum is the International System of Units, exactly. Kilograms times meters over second, isn't it? Impulse. According to Newton's second law of motion, force and acceleration are related by the formula F equal to mass times acceleration. If a constant force F is applied during a time interval, t, then the acceleration produced by the force is. As we already know, and substitution yields, and it can be arranged as follows. The right-hand side of this equation can be recognized as the change of momentum from m, v, 0, to m, v, where v, 0, and v, are the initial and final velocities, respectively, of the body on which a force, F, is acting. The product of the force, F, and the time t, during which it acts is called impulse. Because it contains a force, is impulse a vector quantity? Yes, of course, it is. The unit of impulse is the Newton second. Impact, finally, for today, Let's talk about impact. In our case, we are going to consider it as a collision between two bodies that occurs in a very short interval of time and involves relatively large forces which the two bodies exert on each other. We will only consider direct central impact, in other words, the kind of collision in which the two bodies move along the same straight line before and after the collision. The conservation of momentum principle applies during impact, which enables us to write an equation relating total momentum before impact to total momentum after impact, if we let m, a, and m, b, the masses of bodies a, and b, and v, o, a, and v, o, b, be their initial velocities. The total momentum before impact is given by, similarly, if v, a, and v, b, are the final velocities, the total momentum after impact is, then we have for the system, initial momentum equals final momentum. This equation, by itself, is not sufficient for the solution of problems involving the impact between two bodies, as it contains two final velocities which are not usually known. We have to examine the effect of deformation, and subsequent restitution of the colliding bodies during impact. The extent of restoration of the original shape immediately after collision depends on the elastic properties of the material. If the bodies are completely elastic, they will rebound and return to their original shape, like billiard balls. If on the other hand, the bodies are completely plastic, they will stay permanently deformed, and will travel together with the same velocity, like two lumps of putty, after collision, you see. The measure of the ability of the bodies to regain their original shape is called coefficient of restitution. Mathematically, it is defined in terms of relative velocities, before and after impact. The equation defining the coefficient of restitution, epsilon, is. The value of the coefficient varies from epsilon equals 0 for completely plastic impact to epsilon equals 1, for completely elastic collisions. For instance, for steel on lead, the coefficient of restitution is about 0.12, for lead on lead, 0.2, and for glass on glass, 0.93. We will practice the use of the impulse momentum method with several illustrative examples, but worth to point something important first, before any attempt. Velocities are vectors, right? And therefore, it is necessary to choose a sign of convection. In general, we can assume positive when there is movement to the right and negative to the left, and with this assumption we can be consistent when applying the momentum and restitution equations. Let's apply these concepts to solve engineering problems. Dr. Lorenz Garcia here, thanks for watching. Ciao.